Hello. We'll wait till 6:15 p.m. and then we'll start. So another 5 minutes for others to join. I have allowed your microphones, so you can just unmute yourself and speak or raise your hands at any point of time. All right. Can somebody just confirm if my screen is visible to you and if it is changing when I'm changing the slides? All right. Okay. Thank you, Abdul. All right, let's start the session. Hello, everyone. Welcome to the sixth
Yeah,
weekly.
yes, sir.
Okay, thank you, Sathak. Um, Welcome to the sixth weekly discussion and doubt clearing session of the NPTEL course on concrete technology, NOC24-CE46, which is taken by Professor B. Bhattacharya of IIT Delhi. I am Ashirvad Satpathy. I am a PMRF research scholar at IIT Delhi. And what I do is I take these weekly sessions of 2 hours where we discuss the practice problems that have been given to you in the previous week's um, assignments. And the deadline has already passed for, I mean, deadline for answering the questions has already passed for those assignments. After that, only we discuss those questions. And we also take up the doubts that you might be having regarding the previous week's lectures. There is another teaching assistant to this course. His name is Debojyoti. He usually takes his weekly sessions of 2 hours on Saturdays from 6 to 8 p.m. And I take my weekly sessions on Mondays from 6 to 8 p.m. usually. But I mean, in the current week, due to some prior engagements, I could not take it on Monday. So we got it shifted to today from 6 to 8 p.m. I would also like to inform you that all of the previous week's discussion videos have been uploaded on YouTube, and one of the links have been shared with you in the chat section of the meeting. And the lecture slides that we use during these sessions, we also upload it to to a OneDrive folder, and I've also shared the link of that in the chat box of this meeting. All right. So in today's session, we'll be discussing the week five assignment five questions. Um, the the in this current week, the week five lectures, we discussed about concrete majorly, and what are the factors that affect the concrete mix proportioning, and what are the different methods of designing a concrete mixture. And then we also saw different examples related to the various methods of concrete mix design proportioning. These week five assignment five problems are related to those methods and those lectures. And at the end of the session, we'll also be taking any doubts that you might be having related to week five lectures. So this is the pretext of the question for questions 1 to 4, and it goes as desired 28-day cylindrical compressive strength of a concrete mix is 35 megapascals, where no air entrainment is to be used. The cement used is ordinary Portland cement, and the finest modulus of sand is 2.60. Specific gravity of fine aggregate, coarse aggregate, and cement are 2.7, 2.6, and 3.15 respectively. The density of water is 1000 kg per meter cube. And then they have mentioned the dry rodded bulk density of coarse aggregate, and that is 1700 kgs per meter cube. The maximum size of aggregate or MSA of the rounded aggregate is 19 mm, and the desired slump is 80 mm. The minimum cement content and maximum allowable water to cement ratio for durability are 300 kg per meter cube and zero point 0.5 respectively. The standard deviation of the whole set of samples is given as 4, and they have asked us to calculate the following questions using the ACI method of mix design, and use the tables as given in the PPT slides. All right. And then the first question goes, determine the free water content to be used in the mix in kg per 1 meter cube of the mixture. So options are given for the free water content. Has somebody calculated this question? I mean, the answer to this question? If you have already, I know that the deadline has already passed, so you might have already submitted the answers to it. Has somebody tried to calculate it? Yes, anyone? So actually, this question, I mean, you'll find the lecture slides related to this question in the week 6 lectures actually. So I don't know how it was mixed up with the week 5 lectures. But yeah, the ACI mixed design method of mixed proportion has been discussed in the week 6 lecture. So you'll be able to find the I mean the tables and all of the related data in the week 6 lecture slides. So I hope you use that to calculate your answer. Yes, Srinivasan, you wanted to say something? Does anybody have the answer to this question? All right.
Double
Uh,
two, double two eight. First one.
double to eight. Okay. Did you calculate it?
No, sir. I have my friends is telling about that.
Okay.
So calculate, no calculate.
Okay. All right. Um, we'll go ahead and calculate it as per the ACA method, and let's see what is the answer to this question. So
Okay.
yeah, this is the lecture slide of Module 4, Lecture 4, and this describes the parameters required for mixed design of concrete as per the ACI 211 method. And so the first step itself is estimation of mixing water content and the air content in your concrete mix. All right, and this is the table of data for given for calculation of the mixing water content. For, I mean, for starting the mix design, right? And for that, you need to know the target slump you want to achieve in your mix design, and also the maximum size of aggregates that is being used in the mix design. And also you need to know if you're using any air entrainment, external air entrainment in the concrete or not. So are you using any kind of air entraining admixtures or not? So in our context of the question, we see that it is no air entrainment is involved in this concrete. All right. So it's we are going to use the data as per the table with no air entrained concrete, and um, the maximum size of aggregate is mentioned as 19 mm. It is here, and the target slump is mentioned as 80 mm. All right. So we're going to use this data. No air entrainment. MSA, maximum size of aggregate is 19 mm, and target slump is 80 mm. All right. So if we go to the slides again, we have to select this. We have to select this table, all right, because this is for no non-air entrained concrete, and the target slump lies in this range, 7.5 cm. This is given in centimeters, so 7.5 cm to 8 cm. Ours given is 8 centimeter, right? So this comes under this, and then the maximum size of aggregate in mm is given as 19 for us. So the answer for water content is 205 kg per meter cube. Right? This is pretty straightforward. So for MSA 19 mm and target slump between 7.5 cm to 10 cm, water content is 205 kg per meter cube of concrete. So this is the correct answer to the question, right? So this was pretty straightforward. The second question of this series is determine the air content in percentage by volume to be used in the mix proportioning. Yes, can somebody tell me how do we calculate this?
Tell me, sir.
All right. This is again very straightforward. If you have seen the lecture slides, only in this part, if you can you see my screen with the PDF file of the lecture slides?
Yes, yes.
Yeah. So this was for water content estimation, and after that, we can estimate the air content. And for calculation of the air content, we need only the maximum size of the aggregate. And for that, we know that the maximum size of aggregate is 19 mm. So the air content we need, I mean, that will be added in the mixture automatically, will be around 2%. So the correct answer to this question is, it is 2%, right? For 19 mm MSA. Yeah, I have already shown this. And this is for non-air entrained concrete. And so 19 mm and 2%. For air entrained concrete, you need to also know the exposure conditions. So for mild condition, these are the values for moderate conditions and for extreme conditions. So you need to know the exposure conditions for air entrained concretes in order to calculate your air content. Moving on to the third question, estimate the mean compressive cylinder strength in megapascals. So the compressive strength that is given to you is the 28-day characteristic strength. You need to calculate the mean compressive strength, and the standard deviation is also given in the original question. This is the standard deviation. This is the compressive strength, and the standard deviation of the whole set of samples is 4. Has anybody calculated the answer to this question?
38.3.
Are you guessing it? Can you tell me how do you calculate
Yes,
this?
yes, yes, yes. Guessing that's all.
Okay. Okay. How do you do? I mean, what is your basis of guessing? Okay. The second step in the ACI mix design is itself the calculation of the I mean, average compressive strength of the mixture, because you need the average compressive strength, cylinder compressive strength, in order to calculate the water to cement ratio. So, in order to know what is the cement content, we have already calculated the water content, right? Now, in order to calculate the cement content in the mix, we need to know the water to cement ratio. And in order to determine the water to cement ratio, as per the ACI code, we need to know the target mean compressive strength, mean cylinder compressive strength that we are targeting in this mix. And for that, there are again two data tables that have been given to you. If you do not have the data of standard deviation of the concrete mixes, then you can use this table. So FCR is the average, FCR is the average
Uh,
strength, all right? And FC is the characteristic strength.
That is FCK plus 1.65 into standard deviation. That is the formula using for this one.
No, so that, yeah, the next, if we have the standard deviation values, then we are going to use this. So this is for when we don't have the standard deviation values, then we calculate the average strength based on the type of I mean based on the range of the strength given, 20 day strength given to you. So if it is below to 20.7, this is the formula. If it lies between 20.7 and 34.5, then you have to go with this, or if it is greater than 34.5, then you have to go with this formula. But when you have standard deviation values as we have it in our case, then this the maximum of, so FCR will be maximum of the values from these two expressions. So 1.34s, the 1.65s that you're talking about is from the Indian Standard Code. So we are dealing with the ACA standard right now, and this is the
SCI means that is American Standard of
Ameri
Concrete. American
American
Standard
Concrete
Concrete.
Institute. Yes, American Concrete
That
Institute.
normally they are using for cylindrical sample, isn't it?
Yes, yes.
Instead of cube, they are using cylinder that is 30
This,
centimeter high. Yeah,
yeah, the
ASTM method. They are
cylindrical
using
compressive
ASTM
strength.
method also.
Yeah,
Yeah, yes, sir.
yeah, yeah. So ASTM, yeah, gives you the method of testing, while ACI rules down all the, um, I mean, everything, every methods and every, what to say, the standard procedures of measurements related to the concrete. So, yeah,
Yeah, yes, sir. That is for the testing. This procedure there, ASTM is a very elaborated chapter. Is there too much, specification and everything? How to take the
yes,
sample? How to take the everything is a detail. It is mentioned in the ASTM because I am little aware of this ASTM method because
right, right.
previously I worked in Gulf countries. We used to all this concrete testing, everything done based on the ASTM only.
ASTM, the
In
American
here,
codes.
there, we normally used to take then a 40 cubic meter, four cylinders sample is taking and testing after 28 days and all this thing based on ASTM method.
Right,
Even for taking the aggregate, that, sand, everything, all testing done based on ASTM. Here
right.
in India, we are using this British standard based, isn't it?
Yeah, yeah. Mostly it is based on the British standard, but we have developed our own standards. So we are
This
sticking to the Indian standard. They do have a basis from the British standards. Yes.
Yeah, normally this for cylinder strength it is considering 80% of the cube strength,
Yes.
isn't it?
Right. That is true.
Yeah.
Yes.
Okay, sir. Okay, thank you.
Yeah. So generally, the standard deviation is calculated from a set of 30 consecutive data. Now, you can use either that, or if you have two sets of 15 data each, then you can calculate the S based on those data. I mean, those two sets of data. It was already discussed in the lecture. I will not go into that. But yeah, this is how you're going to calculate your average compressive strength. So let me see if I have it here. All right, I'll just use this. Yeah. So FC is given as 35 megapascals, and standard deviation S is given as 4 megapascals. So average strength, average or mean strength is equal to FCR is equal to maximum of uh, FCR dash, the expression is FC dash plus 1.34S FC dash plus, sorry, not R, FC dash plus 1.34S, FC dash plus 2.33S minus 3.5, plus 2.33S minus 3.5. Right? So we have to take the maximum value of that, and if we put our values in these expressions, then we'll get 35 plus 1.34 times 4 and 35 plus 2.33 times 4 minus 3.5. So that comes out to be yeah, max of 40.36 MPa and 40.82 MPa. So FCR is equal to 40.82 megapascals, right? So the correct answer to this question is 40.8. So this is how you're going to calculate when you're given with a 20-day compressive strength of the cylinder and the standard deviation of all the set of your samples, right?
Sir, if we go for ACI method, that value will be less than this 40.8, isn't it? Because of based on this ACI, if we apply that formula, then I think it is coming for 1.65 into that 5 standard deviation 5, that it is coming to 8.25 plus the characteristic strength is 25. If it is M25, then it is coming 33.25. Actually, I answered this one 33.25 based on ACI, but I made a mistake because of it is mentioned compressive cylinder strength. It is already mentioned in the question, but I
Yeah.
forget that one. Then I straight away I gone to
Okay.
ACI method.
No,
If it is
this is
compressive
the
strength,
ACA method.
definitely we have.
This is the ACA
Yeah,
method of design.
if it is mentioned cylinder, definitely we have to go ACI method. That is
Yeah,
very
right.
clear.
You used it as per the Indian standard.
Yeah. Then I got the answer
Okay, all
38.5.
right.
Actually, 32. Yeah. Because
Yeah.
that table also it is mentioned that M10, M15, that is 3.5 is the standard deviation, M25 4 is the standard deviation, M30 35 40 45 50 etc. All
Yeah,
coming standard deviation is 5.
but you see here
It
in
is
the
5.
question that they have not mentioned
Yeah.
the grade of concrete as such, but rather they have
Yeah.
mentioned directly the cylindrical compressive strength. When we mention the
Yeah.
grade in terms of
Yeah.
M30, M40, that is as per the Indian standards. But if
Yeah.
you,
It is
yeah, and
correct. Because,
yeah,
yeah. Thank you, sir.
okay. Okay. So the fourth question in this series was the water to cement ratio that yields the required compressive strength is, and this was a, data entry type question. So there were no options given in this question. So we need to calculate the water to cement ratio. Has anybody calculated this already? Can you tell me the answer? All right. So after you calculate your compressive strength, mean compressive strength, then you can go to this table here. So you have the average compressive strength, and then you have the water to cement ratio by weight for non-air entrained concrete and for air entrained concrete. And ours is the case of non-air entrained concrete, right? And our mean compressive strength lies somewhere in between 40.82, right? So for 40 megapascals mean strength, the water to cement ratio recommended is 0.42. For 45 megapascals, the water to cement ratio is reduced. It is 0.38. Now we need to calculate the water to cement ratio for 40.32. How do you do that? It's by linear interpolation, right? Linear interpolation. So we need to linearly interpolate this data in order to find out the water to cement ratio in this case. So we know that for 40 megapascals, water to cement ratio is 0.42, right? For 45 megapascals, water to cement ratio is 0.38. So for 40.82 megapascals, the water to cement ratio will be, it's normal linear interpolation method. So 0.42 plus 0.38 minus 0.42 divided by 45 minus 40 into 40.82 minus 40. So this will be the water to cement ratio. If we calculate this value, how much is it coming? Can somebody can tell me the answer?
0.413.
Yes, the answer is 0.413. So you can just go ahead with 0.41. So this is the water to cement ratio that comes from the mean compressive strength that we have already calculated. So I guess the given answers were uh, a range between zero point 0.4 to 0.45, I guess. So this was the accepted answer range, I guess, in the question assignment. Although this range is huge, but yeah, anyway. So this is how you calculated the water. And these were the 4 questions from this series. I hope that was clear to you. Now the 5th question was, in the in the fresh state, concrete behaves as a Bingham fluid, Newtonian fluid, none of the above, Newtonian in its fresh state, and Bingham in its hardened state. Which of these options is correct and why?
Yes, first one, Bingham fluid.
Bingham fluid. Okay, thank you. Yeah, that's the correct answer. What is a Bingham fluid? Can you explain? I mean, I want to know. Okay, let's not ask you this way. What is a Bingham fluid? What exactly makes concrete a Bingham fluid and not a Newtonian fluid? How do you differentiate that the concrete behaves as a Bingham fluid and not a Newtonian fluid? Yes, Abdul, or anyone else? Do you have, I mean, any explain? Yeah, that's the correct answer. Actually, it behaves as a Bingham fluid. But what is the basis of your differentiation between the different types of fluid and how concrete behaves in its fresh state?
This is based on concrete bleeding, something like that.
Okay, not bleeding exactly. It's based on the flow characteristics of concrete in its fresh state. So when concrete is plastic and in its fresh state, how the concrete deforms and how the concrete flows. Based on that, you characterize the type of fluid behavior it conforms with. Do you know any
Yeah,
examples of Newtonian fluid?
it, it is connected with the capillary force also connected with this one.
No,
Concrete
no.
to bleeding and capillary. That's a bleeding and this water is coming upside. That is, because of the capillary force, something like that.
Not exactly. So, see, we do not characterize the bleeding or the segregating mixes as any fluid behavior because those are not stable mixes. So, you won't be able to I mean, categorically say that this given concrete mix conforms with this kind of a fluid behavior. So, because with bleeding, you know that the mix is no more homogeneous in nature. And when the mix is not homogeneous, it will show different type of behavior at different stages or at different regions within the mix itself. So we do not characterize, I mean, straightforward reject any unstable mixes, any mixes that show the signs of bleeding or segregation. So when we are talking about the fluid or the rheological behavior of concrete, we are only dealing with stable mixes. We have totally ruled out the possibility of bleeding or segregation for some time now. And then we are characterizing the concrete as a Bingham fluid. Now, what is a Bingham fluid is, in case of Newtonian fluid, we know that fluids have a very low shear strength or negligible shear strength, right? So when you apply a shear force or a shear stress to a fluid, it will flow, right? So when it flows, it loses its, I mean, it loses its shear strength, and it deforms against the applied force, right? Now, while it is flowing, it might so happen that due to the fluid behavior itself and due to the mm, I mean resistance to the flow between the interlayers of the fluid, it it is showing some kind of a shear stress, right? And this resistance to flow within the layers of a given fluid is known as viscosity. So if we say that concrete is viscous or any fluid is viscous because it has some resistance while it shows some resistance while it is flowing, right? And then the shear stress that is experienced while the fluid is flowing is known as, I mean, it can be characterized at the shear stress at a given shear rate. So if I draw the plot between shear rate is basically the rate at which you are applying the shear strain to it, right? So shear rate versus the shear stress plot. The Newtonian fluid will have a linear behavior with increasing shear rate. The shear stress also linearly increases, and at zero shear rate, it has a negligible shear stress. And the example of this is Newtonian fluid behavior. Examples of Newtonian fluids are, it's normally water. Water is a Newtonian fluid. It doesn't have any shear stress at rest, but when you apply a shear rate or you apply shear force to it, then it starts flowing and the shear stress increases as you increase the shear rate linearly, right? In case of Bingham fluids, what happens is the plot goes somewhat like this. So again, this is linear, but they do have some shear stress when it is at rest. So in order for a Bingham fluid to flow, we need to overcome this initial stress, um, and then only the Bingham fluid will start to flow. And this initial stress or the intercept on the y-axis of this plot is known as yield stress. So essentially, concrete is a yield stress fluid. So I'll explain it to you what is the difference between Bingham fluid and yield stress fluid also. But yeah, in order to make Bingham fluid deform, we need to um, overcome an initial shear stress known as yield stress, right? Now this y-intercept is the yield stress, while the slope of this plot is known as viscosity, right? The slope of this plot will give you the viscosity. So for Bingham fluids, the viscosity is constant throughout. For Newtonian or for Bingham fluids, the viscosity is constant throughout the shearing process. As you move on, as you keep on increasing the shear rate, the shear stress increases, but leniently so, and therefore the viscosity is constant throughout. Now, there can be different types of yield stress fluids, and concrete also shows different types of yield stress behavior depending upon its mixed design parameters. So it can so happen that it is linear, or it shows a non-linear behavior and goes somewhat like this. And it shows it can so happen that it shows a non-linear behavior and it shows somewhat like this. So this is the again the shear stress versus the shear rate plot, right? This is the yield stress. When you show a linear behavior in yield stress fluids, this is the Bingham fluid, as we discussed in the top figure as well. This is the Bingham behavior. So the viscosity is constant throughout. But in this plot, the viscosity is increasing as we increase the shear rate. So the stress is also increasing, but again, the viscosity, you can see that the slope is increasing. So as you move on increasing the shear rate, the viscosity is also increasing. And when this type of increase in viscosity is observed, we call the fluid as shear thickening fluid. So the effect, it seems like as we applied increasing amount of shear, the fluid somehow appears to be thickening in nature. It becomes thicker in nature. So that's why it is called as shear thickening fluid. And when the viscosity in the upper case, you can see that the viscosity is constantly decreasing, right? When the viscosity decreases, it is called as shear thinning fluid. You can experience this kinds of different types of fluid effects. No, I mean, even though we are discussing in this question that in fresh state concrete behaves as a Bingham fluid, but not always so. I want to emphasize here that not always does concrete conform with a Bingham behavior. It sometimes shows shear thickening fluid behavior also, as in the case of low water to cement ratio. At low water to cement ratio, concrete sometimes depending on the mixtures, like the powder content in the mix, or if you have any added any fine materials like pozzolanic or supplementary cementitious materials in the mix, then depending on the mixture design as well, not just because of the water to cement ratio, but depending on the other constituents in the mix as well, concrete might show a shear thickening behavior. Shear thickening, right? And when you add very high amounts of superplasticizer in mix, high superplasticizer in mix, then concrete might show. Again, it depends on other constituents as well, but I'm just mentioning might show shear thinning effect. All right. So not always does concrete show a typical Bingham behavior. It can show a shear thickening or shear thinning effect also, but concrete is always be going to a yield stress fluid. You can decrease the yield stress by, optimizing the different parameters, but it will have some certain amount of yield stress in it. It will need an initial stress in order to start flowing. So, yeah, that's the whole summary of how concrete behaves in its fresh state. Do you have any doubts regarding this? All right. Moving on. Um, I guess this is the last question of this assignment. What is the mixing time for 3 meter cube of concrete according to Indian Standard 4925 1968? Is it 1 minutes, 1.5 minutes, 2 minutes, or 2.5 minutes?
As per Indian standard, it is 2 minutes.
Yes, that's the correct answer. It is 2 minutes. Thank you, Abdul. Yes, this was again straightforward. And yeah, that was the end of the assignment questions discussion for the week um, 5, sorry, week 6. And if you have any doubts, then we can take it up now regarding the previous week's lectures, because we do have a lot of time left actually. So if you have any doubts, let's discuss those. Yes, anybody has any doubts
No, sir.
regarding this discussion or any other previous lectures or any of the assignment questions of the previous lectures? Okay.
Sir, for this concrete pumping and all these things, plasticizer is adding certain, according to the calculation and all these things.
Uh-huh.
This will make any adverse effect for the concrete strength? If this plasticizer adding more and all these things, it will make any
Yes.
adverse effect for the structural strength and all these things.
Um, uh, I mean, see, it depends on the amount of plasticizer you are adding, and what is the what is the behavior of concrete in its fresh state. It is always the fresh concrete in its fresh state is partially responsible for its durability properties as well, not just strength but its durability as well. So if you're adding too much of the admixture and the concrete is prone to bleeding or segregation, then that will create a lot of voids in the mix, and it will create an inhomogeneous mixture, and therefore the heavier particles, that is the aggregates, will settle down, while the paste and the mixing water or the pore water will be standing on top of it. So you'll see that the mix will be inhomogeneous, and that will affect the strength and durability. So it depends if you're adding admixture or not. I'm not talking about admixture in general, but superplasticizer, as you asked. If you're adding superplasticizer in the optimum content, meaning that whatever is your target slump, you're adding only that amount of superplasticizer, which is making you able to achieve your target slump without any effects of segregation and bleeding. Then it should not affect your strength. Now, if it is affecting your strength, then you need to see if the superplasticizer is compatible with your cement and the mixture itself. All right. And maybe you can make some tweaks because commercial superplasticizer come with some amounts of retarder in them. So it should not affect your long-term strength, as in 28 day strength or so on. But if it is affecting your early strength a little bit, then you could decrease the retarder in the superplasticizer mix. That's one way to do about it. But as such, if you're adding superplasticizer in optimum content as per required, and you're seeing no negative effects of instability in the mix, then it should not affect your strength.
Is this super plasticizer, is it inert material or any chemical action is taking in this?
It has both. Yeah, it is not an inert material actually. So the chemistry of superplasticizer is such that it absorbs on the surface of the cement particles and other particles, and it disperses them. But while dispersing them, it doesn't only do this as a physical phenomena, it also does it as a chemical and a physicochemical phenomena. So it's a mixture of physical and chemical forces acting within the cement mixture itself. So it is not an inert material, I would say. It doesn't react with the cement itself, but yeah, it does affect the rate of chemical reactions that go within the cement. So it takes part in the chemical reaction, not directly, but indirectly so. Yes?
Okay. Okay. Thank you, sir.
Okay.
Yeah, sometimes this concrete adding some retarding agent for initial setting time and all these things to postpone.
Right.
Sometimes some chemicals adding retarding agent is adding. This will make any effect for the strength or any other effect for the concrete. Retarding agent adding for just
Yes.
postponing the initial setting time.
Yes. So retarders generally affect your early strength. 1 to 3 day strength might be affected. Generally, if it is added in very low amounts, retarder is not added in the amounts comparable to that of superplasticizer. If I mean, roughly speaking, in very crude comparative terms, if you're adding around 1.5% of or 1% of superplasticizer, then you would be probably adding retarder of around 0.05% or so by the weight of cement. So it's very less in the superplasticizer, or if you're even directly adding it, then it is very less in amount. But even if at that amount, it does affect sometimes the early strength of it, early strength of the concrete. Mostly 1 to 3 days. Now, if you add a lot of retarder to your mix, then it might totally hinder the reactions in the cement, and your later strength might be affected as well. But yeah, I mean, it comes as a compromise of uh, flow, uh, setting time, and early strength. So it's going to be a compromise between all the three all the time. If you want to achieve higher flow, then you'll have to compromise on the early strength a bit. Or if you want to achieve longer setting time, then again you'll have to compromise on the early strength a bit.
Sir, good evening, sir.
Yes, good evening, Srinivas.
Actually, superplastic is using only for increase the workability.
Pardon?
Actually, superplastic is using for only increase the workability only.
Okay, yes.
Or
Are you asking me
other
or telling
phenomena
me?
is not. Is it? Sir, for using only in workability, superplastic increase the workability.
Yeah, I mean, so the main motive or objective of adding superplasticizer to your mix is that all the powders in your concrete mix, meaning the cement, or if you're adding any pozzolans or supplementary cementitious materials, when the powders are so fine, they are always in an agglomerated state. Now, when you add superplasticizer, it acts as a dispersant, and it disperses uh, all these fine particles. When you have a higher dispersion, then when they were in a these particles are in an agglomerated state, what they do is they trap some of the water that you're adding, the mixing water that you're adding to your mix. So the ultimately the mixing water is not totally available for achieving the target flow. When these particles, the agglomerates are broken down, and these particles are totally dispersed, then they won't be they won't be entrapping any water. So the water will be available for the flow, for the workability, and also for the hydration as well. you know so that is how it is. So the main objective of adding superplasticizer is to disperse this agglomerates that are forming in the powder in your concrete.
Thank you, sir.
So either you, I mean, as the name itself suggests, plasticizing effect. So you make your concrete more plastic, or you know that superplasticizers are also called water reducers. So in you if you want to decrease the water content in your mix, then also you can add a super plasticizer to achieve the same workability or same flowability. Sorry.
Thank you, sir.
If you talk about chemical admixtures in general, then some of them, I mean, a lot of the chemical admixtures also take part in the chemical reactions. They, like, let's say, as we discuss retarders, so they do retard the cementitious reactions inside the concrete. In case of shrinkage compensating admixtures, so different admixtures have different methods of action. Like the shrinkage compensating admixtures, they reduce the surface tension of the water, so that the I mean the capillary forces are reduced because the water surface tension is reduced, and if the capillary forces are reduced, the shrinkage will be reduced too. So depending on the type of chemical admixture that you're using, the action will be also different. The mechanism of its working is also different, and its correlation with strength and durability will also be different. I mean, its effect on strength will also be different. Anything else you want to discuss? All right. The session will go on till 8 p.m. So you're free to ask any doubts or any questions, and we can discuss them till that time. If you don't have any doubts or questions, then you're free to leave the session.
If we add water reducing agent, is there any advantage for saving the cement? Because workability can increase if we add a water reducing agent. That means water can be reduced to the mix. Then same time we can get the workability also. In that case, there is some advantage for saving the cement content.
Mm, I mean, you want to save the cement content by adding super plasticizer.
Exactly, because if we are adding water reducing agent, that means the water can be reduced if we add the water reducing agent. In that case there is some changes in the water cement ratio. That means if water is less, then cement content also can be proportionately can be reduced, isn't it? In that case, if we add water reducing agent, then is there any advantage for saving the cement
Okay,
content?
okay. Cement content is not only governed by the workability itself. Cement content is majorly governed by the durability performance or the durability prescriptions in the code. I mean, at least I'm talking about the Indian standards, and the minimum cement content is generally based on the durability requirements. All right. So cement content, I mean, even if you save on the water, right? So you'll be able to, let us say you're doing a mix at zero point 0.5 water to cement ratio, and so 200 kg and 400 kg, 200 kgs of water and 400 kg of cement, let's say. Now, if you are adding admixture to it, super plasticizer to it, you don't require 200 kgs of water now. So you'll be able to reduce your water to cement ratio. And in a way, if you reduce the water to cement ratio, you'll be able to achieve higher strengths, right? Because if you're reducing the water to cement ratio, the voids are reducing, you'll be able to achieve higher strength. But you need not reduce the cement content in that case. Because you're adding super plasticizer, you're achieving the same flowability at a reduced water content. So it's a trade-off between the water content and your addition of the super plasticizer. Cement content, you can again, yeah, you can reduce because you have a greater flowability, so you can reduce the paste content, the whole paste content a little bit. But it is not. I want to emphasize on the fact that it is not just governed by the workability or the flowability requirements. It is the cement content has to be checked with the durability requirements as well in the mixture. Like in the case that we discussed today, also you can see in the first question. You see that here
Yeah,
it
yeah.
is a, yeah, it's a minimum cement content is mentioned and maximum allowable water to cement ratio, right? So these maximum
Yeah.
allowable water to cement ratio or the minimum cement content are based on durability requirements.
Yeah, it is correct. All the mixed design there is a minimum cement content. This is mentioned different type of mix.
Right. Yes.
It should be minimum that match above that quantity that can be achieved from this reducing agent, and all this and some part we can achieve, but
Yeah.
minimum always should be there.
Yeah. Right.
Yeah,
That's what
that's
it is.
that's
So in any case, even if you try to reduce the cement, ultimately what you're trying to do is you're reducing the paste content, right? So when you're reducing the cement, because water is already reduced because you added super plasticizer, now you're reducing the cement, so you're reducing the paste content. So again, I mean, it's a trade-off between what you want to, I mean, how much you want to compromise on the workability, because um, at the same water to cement ratio, sorry, at the same, I mean, at a given, for a given mix, let's say as we discussed, 0.5, so 200 kgs of water and 400 kgs of cement. Now, if you want to add some super plasticizer to this, you can keep the cement content same and reduce the water. So you're saving on the um, uh, water to cement ratio, so you're increasing your strength ultimately. So that's one way to do it. Or else, if you want to also decrease your cement content, then you're essentially reducing the paste content, the paste volume in the mix, and increasing the aggregate volume in the mix. So then you'll see a little lesser flowability than that, because it is the cement paste that keep all the aggregates in suspension in the, I mean, the concrete mix, right? So the flowability will also reduce if you reduce the cement content.
okay. Okay, sir.
Yeah. Anybody else has any doubts? Yes, any more questions related to the sessions or lectures or any of your site experiences?
Sir, while pouring concrete,
Yes,
what is the maximum temperature considered, ambient temperature considered while pouring the concrete in Indian conditions? What is if it is ambient temperature is a certain high, then it is not good for the pouring concrete.
right.
In India, what is the maximum temperature considered as per Indian standard and all this thing?
Um, so I'll tell you this way that if you have very high temperatures like uh, till 40-45 or so, it's all right? But if you are going beyond 50 or 60 degrees Celsius, then you will have to, I mean, it will affect the reactions in your concrete. And therefore, you need to add, I mean, take some measures in order to reduce the temperature in the concrete. One way to go about it
Yeah,
is to use cold water
by
for mixing.
adding chilled water and ice and all these things, adding mixing
Right.
to control that is a concrete temperature can be controlled, but ambient temperature we cannot control, isn't it?
Ambient temperature cannot be controlled. So you have to, I mean, even if you have to do a concreting at a very high temperature, you have to take these measures in order
Yeah,
to, yeah,
timing should be adjusted like that.
yeah, timing should be adjusted, and you can just, I mean, take these measures like use cold water or something like that in order to reduce the temperature in your concrete. As long as
Yeah.
you're doing proper curing and I mean the temperature inside the concrete is reduced, I mean it is reduced to normal rates, then it won't it should not affect your strength or durability as much.
Okay.
Yeah.
Sir, good evening, sir.
Yes, good evening.
Sir, gel porous affected through directly related to creep and shrinkage, sir.
Yeah.
How, sir?
Um, okay. I mean, how so as in what do you want to, what exactly is your question? I could not get it.
Actually, gel porous
Gel pores, yes.
and directly affected to creep and shrinkaging, sir.
Yes. Creep,
How, sir?
yeah. Okay, so when you when you add water to your concrete, the water remains in different types of pores, and there, as we have discussed in the previous sessions as well, different pores. Now, um, some the water that is majorly in the voids or the capillary pores, that can be utilized for hydration, and so the water comes out of these capillary pores with the increasing age of concrete, and when the water in the nearby the unhydrated cement is reduced, this water keeps on coming out from the capillary pores and it is getting used in the hydration. Some of it also gets evaporated or expelled out of the capillary pores, and thereby we experience shrinkage, as we already discussed. And when the hydration products are formed, so some of this water is also adsorbed onto the CSH gel, and then some of the water is also trapped in the gel pores itself. Now, this water is generally not expelled out of these pores, and since the water is present in this pores, so the pores have a certain capability of deformation, right? When you
Okay,
applied
sir.
a constant load to the concrete, I mean, even if it is under its weight, so with passage of time, the concrete tends to creep, tends to deform under this constant load. And this creep can be characterized in the terms of the deformation in the gel pores itself.
Thank you, sir.
Yeah. All right, if you have any other questions, then we can discuss, or else we can close the session for today. So does anyone else have any questions? All right. All right, then we're closing the session for today. We'll meet again on Monday from 6 to 8 p.m. Thank you.
Thanks.
Okay, thank you, sir.